I'm often asked by experienced Sketchpad users how to use Sketchpad to make a decision. Sometimes the question is asked, how can I create an if-then-else construction? In this video, I'll describe a general and powerful solution for these sorts of questions. The solution involves something called Boolean Algebra, which is a branch of mathematics devoted to true-false operations and decisions. In this example, we'll use Boolean variables and operations to decide whether this triangle is an isosceles right triangle. We'll begin by deciding whether angle ACB of the triangle constructed on this geoboard is a right angle. By the way, if you don't know how to construct a geoboard, use the Help menu and look it up in the Reference Center. So we'll go ahead and measure the angle, but now we need to determine whether it's a right angle. So we need a calculation based on this 76 degrees that comes out to 1 if the angle is exactly 90 and comes out to 0 otherwise. To simplify our calculation, we'll first subtract 90 from the angle. So the result of negative 14 shows that it's not a right angle. We'll then use this result as input for the signum function, which, as you can see, returns negative 1 for negative values, 0 for 0, and positive 1 for positive values. So if we use this value as input for signum, calculate from the Functions menu, choose signum, input the negative 14, we will get negative 1 as expected, showing that x is less than 0. But we want a result that's a little different from this. A Boolean result must be 1 for true and 0 for false. So this is going to take us 2 more steps. The first step will be to find the absolute value of this calculation we just did. So let's go ahead and do that. The absolute value of this now gives us a value of 1 if it's less than 0 or greater than 0, and a value of 0 when it's equal to 0. But we want to reverse that. So the easy way to reverse that is going to be to calculate 1 minus the value we have here. And this should give us the appropriate value so that, for instance, when we have a right angle here, the output is 1. So that says it's true that we have a right angle. Now it's false that we have a right angle. True, false, false, true. Okay, having solved this problem, let's turn our solution into a custom tool. We could make a tool to detect 90-degree angles, or we could make a tool to detect the value of 0 that we had at this second step. The second choice will be more widely useful. So that's what we'll do by selecting this calculation as the input for our tool and this calculation as the output. So we'll create a new tool, show its script view, and we'll name our tool x equals 0 because this conducts the Boolean test to see if x is 0 and returns a value of 1, a value of true, if x is equal to 0. Now we called the tool x equals 0, so I should also call the input value x. So now we have a tool to determine whether a particular value is 0. Having made this tool, we can use it for other purposes. For instance, we can determine whether sides A and B are equal by measuring both of them, subtracting one from the other, and using our tool to determine whether the two sides are equal. So we see now that the two sides are equal only in certain configurations of our triangle. And some of those configurations do have a right angle. This is our right angle result, but don't have equal sides. We have false for the two sides being equal, and others have a right angle and also a true result for the two sides being equal. So to determine whether we have a isosceles right triangle, we need to know if both of these values are true if we know that it's both a right angle and we know that the two sides are equal. So we'll finish by doing a Boolean calculation with these two Boolean results to determine if they're both true. This operation is called the AND operation in Boolean algebra, just as we say in natural language that angle C is 90 and the two legs are congruent. An easy way to do this calculation is simply to multiply the two values, because the product of these two values is going to be 1 only if both of them are 1. In other words, a true result only if both of these are true. So let's go ahead and do that calculation. Calculate this Boolean result times this Boolean result. And indeed, we get a Boolean result of 1, which says that we do have an isosceles right triangle if either of these two pieces is false. For instance, here we have a right angle, but different length sides. Here we have the same side lengths, but not a right angle. So this is successfully determining whether both are true. In other words, we've created a test to determine whether the two conditions are true, whether we really have an isosceles right triangle in this figure. As with the x equals 0 tool, we can turn this operation into a tool as well. This is a general tool for finding the logical AND of two values. So our givens are the two values we want to check, and our result is the logical AND. So we'll turn this into a tool. We'll call it the AND tool. And let's identify the input values, let's say, as P and Q. So let's review. We've used a calculation to determine with Boolean algebra whether angle ACB is a right angle. Call that proposition P. We've created a Boolean tool to automate that process in the future. We've used that tool to determine if two segments are congruent. Let's call that result proposition Q. Then we've used a calculation to determine if both P and Q are true. And finally, we've created a tool to perform the Boolean AND operation. So we now have a beginning set of Boolean tools, an x equals 0 tool, and an AND tool. Here are 3 challenges for you. Create a Boolean comparison to determine whether two values x and y are equal. Challenge 2, create a comparison tool to determine whether x is greater than 0. Finally, create a tool to perform the Boolean OR operation that determines whether one or the other of propositions P and Q is true. The Boolean logic tools that come with Sketchpad, which you can find in the Sample Sketches and Tools section of the Help menu, contain tools like these and much more. In a later video, we'll see how to use these tools to control constructions or to display feedback to the person using your presentation sketch. For this example, the feedback might be a message that says either yes, this is an isosceles right triangle, or no, this is not an isosceles right triangle. In this video, we'll look at constructions that sometimes exist and sometimes don't, based on the configuration of the sketch. One of the uses for this kind of construction is providing conditional feedback to the user, telling the user whether or not they've got the sketch in the correct configuration. The basic technique involves using the signum function, perhaps embedded in the Boolean logic tools, perhaps not, to solve the problem. So here's an example. We'd like in this triangle to tell the user the angle is a right angle, the angle is an acute angle, or the angle is an obtuse angle, angle C. So I've got 2 of the appropriate messages here. Let's add the third message that we want to be able to show. And then let's look at how to actually show these messages. So we can say angle C is an obtuse angle as our third message, and we want to display one of these three messages depending on the condition of the sketch. Well, first we have to evaluate the condition of the sketch, so let's measure angle ACB, and 112 degrees. Okay, that's an obtuse angle. How would we know that? Well, it's greater than 90, so we're going to evaluate it by subtracting 90 from it. Now, because we may have directed degrees as our angle measurement, in fact, in this sketch we do, we may have negative values for angle ACB, so we really want to use the absolute value of angle ACB in this calculation. So let's go ahead and calculate, starting with the absolute value of angle ACB minus 90 degrees. So that gives us a result of 26 and some odd degrees. Okay, 27 degrees, because that's greater than 0. This is an obtuse angle. If we're an acute angle, it would be less than 0. A right angle would be exactly 0. So let's use the Boolean tools that we worked on last time and that are available from the Help menu through Sample Sketches and Tools to determine whether this is greater than 0, in which case it's an obtuse angle. So we'll use the A is greater than 0 tool on our calculated value, and the result comes out to 1 because indeed that calculated value is greater than 0. Now it comes out to 0. So when this value is 1, we want to display the obtuse angle message. Let's pick a point at which we'll display our message. Well, we could put it right here. And we'll actually display the message by dilating this point either by a scale factor of 1 or by a scale factor which prevents it from existing. For dilation, we'll need a center point, which I'll put down here and call the center of disappearance. And the dilation that we'll use is going to be based on a calculation of 1 over the value that tells us whether it exists or not. So the dilation scale factor right now is 1, but if I drag point B so that we have an acute angle, we have an infinite dilation, which means the point won't exist. So here it does exist because angle C is obtuse, so we can go ahead and mark the center as the center point, double-clicking it, select the point where we want to display the message, dilate it by this scale factor, which is going to be a dilation by 1. A dilation by 1 puts it right where it is. And we'll select also the message we want to appear, and holding the Shift key down, merge the text to the point. Now this message appears only when it's obtuse, not when it's right or acute. So let's do the same thing now for a right angle. So now we have a right angle. So we need to dilate this point by a different scale factor based on whether the value is equal to 0. So that's our A equals 0 tool. So the A equals 0 tool determines whether or not this value is 0. It is at the moment, so we get a true result of 1. We do a similar calculation, 1 over this Boolean value. So our scale factor will be 1. Move the center of disappearance over to here so we don't get in the way later. We're going to dilate now by a different scale factor, by this one. And this is the point to which we want to attach the right angle measurement. Remember to use the Shift key again to merge the text to the point. So finally, when it's an acute angle, both of these are false. Both dilations are infinite, so neither message exists here. But we'll add the third message now based on when A is less than 0. So when our value is less than 0, as it is now, we have an acute angle. We'll do our calculation, 1 over the Boolean value. So now we have the amount to dilate by for the third message, transform dilate by this measurement, and attach to that the acute angle message. Now we don't need to show these points anymore, so I'll hide the points and hide that one as well. So now we see the message. It's an acute angle, it's a right angle. There's the point that didn't exist a moment ago. It exists now, but we'll hide it. And one more point that didn't exist a moment ago, and we hide it. And now we have a nice message that shows whether the angle is acute, right, or obtuse. Okay, so that's one way of making points exist or not exist. We could use them to show messages, as we've done here. We could also use them to do actual constructions. As our next step, let's do an actual construction. And I'm going to hide the unnecessary parts of this so that we only have the message about whether angle C is acute, obtuse, or right. And we'll use this calculation in a moment to get to do something with the square on side C of our triangle. So let's look naively at what happens when we put a square on side C of the triangle. Let me double click point B to make it the center of rotation. Rotate point A about it by 90 degrees. Okay. So there's another vertex of our square. Make this the new center point. Rotate this by 90 degrees. Okay. And there are the two other vertices of our square. We can use the polygon tool to actually construct the square. So there's the square on side C. Now, to the reason to think about conditional constructions here. What if point C were over here? Now the square is on the inside of the triangle instead of on the outside. So we'd like to use what we know about the triangle to put the square on the right side. So it's always on the outside of the triangle. Let's see how we would do that. The angle is now 90 degrees. Let me drag point B now. And now we've gotten to the inside condition, and this happens when angle ACB is negative. And that's actually what was happening over here as well. Angle ACB is now negative. So if angle ACB is negative, we want it on this side. If angle ACB is positive, we want it on that side. So let's see how we would do that. We did this with a 90-degree rotation. When angle ACB is negative, we'd like to use a negative 90-degree rotation to get to the right spot. We can't use this actual measurement because it might not be exactly 90 degrees. In fact, whenever it's negative, we want a negative rotation. Whenever it's positive, we want a positive rotation, but it's not always by this angle. Well, the signum function comes to our rescue. Let's do this calculation. Start with the signum function of this angle and multiply that by 90 degrees. When the signum function is -1, that will give us negative 90 degrees, which is the rotation we want. When signum is positive, that'll give us positive 90 degrees, which is also what we want. So this is actually an easier way than bothering to use the Boolean functions for this particular instance. Okay, so point B is the center point. Point A we're going to rotate, transform, rotate by this angle, and double click this to make it the center, rotate point B by that same angle. And these are the vertices that should work in all circumstances. So let's get rid of these that don't work, that we're not so happy with. Use the polygon tool to put these in place and see if we got it right. There we go. Seems to work perfectly. Let's see. Ah, nice. Okay. We would also like to create a tool that actually does this. So I'll select the entire construction, create a new tool. We'll call a new tool an outside square. We'll show the script view. So let's use that tool. If we start from point A going counterclockwise, that will be B and then C. And if we start from B to C and then A, we get to see a construction in which the squares always stay on the outside of our triangle. So that's nice for looking at the Pythagorean theorem in different situations and being able to manipulate things cleanly and have it stay the way we want it to stay. So let's look at what we've done. We've displayed some feedback about angle ACB by creating points that exist only when we want them to. We've constructed a square that's always on the outside of a triangle using the signum function, and we turned that into a tool. So here are a few challenges for you as well. A quadrilateral on a geoboard that tells the user whether they've got a rectangle or not. Take the three outside square construction, measure the areas, and display a message to tell whether c squared is greater than, less than, or equal to a squared plus b squared. And finally, try yourself creating a new Boolean tool with three givens to decide whether a is less than or equal to b, which is less than or equal to c. So there's some nice challenges for you.